We continue our lecture on the volumes of solids of revolution by taking another example and remembering that the volume element is pi y squared dx, and the fact that the volume is an integral of dV, that means integral of pi y squared dx, where y as a function of x is defined very clearly. Now, I have taken as the next example the volume of a cone because again this result is known. We are going to generate a cone by revolving this area. Here we have a right angle, a triangular area in which we have taken a right angle triangle. We are going to revolve this area about the x axis by 360 degrees, full revolution, and generate a solid that is going to be a cone. After the revolution has been carried out, we will get a cone. I have tried to give a good depiction of the resulting cone. This is the base area of the cone. So, it is by now clear. In fact, when I was a student myself, I used to take a piece of paper, stick it to one stick of the broomstick, paste it, take a lot of pains to form a small area and then rotate it in my hands. And you can indeed do that yourself to see that the volume of revolution indeed forms. If you give a very quick turn, you see a cone being formed. That I recommend to students who are interested, but that is also imaginable. I mean, one need not try. Now, we are going to find out the volume of this cone. I have given the cone the following characteristics. This is h from the center of the base circle. This is h, and this is r, that is the radius of the cone, and the semi-vertical angle as this is known as theta. So, the integration is very simple. It is not going to be tough at all. We need to evaluate pi y squared dx from 0 to h up to this point. This is the last value of x. Mind you, not up to this. This is just a 2D picture, somehow converted to 3D so that you understand. So, the integration is from 0 to h. So, we write 0 to h pi y squared dx. Now, the question is, we will have to take this y as a function of x, this y as a function of x. One can see that y is equal to mx, form of line. This is a line passing to the origin. So, its equation is y is equal to mx type, where what is my friend m is the slope of this line, that is tan of theta. M is tan theta, and that tan theta is nothing but r over h. So, r over h x. So, this is pi out 0 to h. Y, as I said again, mx, m is r over h. So, r square over h square and x square, because that is y, r over h x. And of course, with respect to x, that is the integral we have to evaluate. There is nothing wrong there. This entire expression is for y square. Rx over h is y square, r square, x square, h square. Now, these can be taken as pi. R square is a constant as far as this integral is concerned. H square is out here, and we just have to integrate 0 to h x square dx. One can see that this is nothing but pi r square h square. So, pi r square over h square into x cube by 3 integrated from 0 to h. So, that will be h cubed by 3. It's a very simple algebra. So, we have indeed 1/3 pi r square and h. This is h cubed here and h square here. So, this just simplifies to 1/3 pi r square h. And this is of course a result that is known to us because we have done cones again in class 11, 12. The volume is 1/3 pi r square h and the curved surface area is pi r L, where L is nothing but this length. That we'll do separately when we are going to do areas of surface of revolution. We are now dwelling on volumes of solids of revolution.